Secretary, Shri Vaishnav Vidyapit Trust, Shri Kamal Narayan Ji Buradia, all respected head of the institutions, head of the departments, my esteemed colleagues and dear students. Foremost, I request all the dignitaries and audience to join traditional auspicious lamp lighting ceremony and Saraswati Vandana as a tribute to Mother Saraswati, the goddess of knowledge. Technical team, please proceed.
असतो मा सद्गमय तमसो मा ज्योतिर्गमय मृत्युर्मामृतं गमय ॐ शान्ति शान्ति शान्तिः या कुन्देन्दुतुषारहारधवला या शुभ्रवस्त्रावृता या वीणावरदण्डमण्डितकरा या श्वेतपद्मासना या ब्रह्माच्युतशङ्करप्रभृतिभिः देवैः सदा वन्दिता सा मां पातु सरस्वती भगवती निःशेषजाड्यापहा.
Welcoming the guest is a part of code of conduct for the Indian culture. I request our Honorable Chancellor and Vice Chancellor Sir to please welcome our Chief Guest, Padma Shri Dr. P. Thank you, sir. National Science Day is celebrated in India on 28th February each year to mark the discovery of the Raman effect by Indian physicist Sir C.V. Raman on 28th February 1928. I request our Chief Guest Dr. P. Pradeep and our Chancellor and Vice Chancellor Sir to pay the tribute to Bharat Ratna Sir C.V. Raman. Thank you, sir. Life of Sir C.V. Raman is inspiration to all of us. Now, we will go through the glimpses of his life.
One of the most prominent Indian scientists in history, C.V. Raman was the first Indian person to win the Nobel Prize in Science for his illustrious 1930 discovery, now commonly known as Raman effect. It is immensely surprising that Raman used equipment worth merely rupees 200 to make this discovery. The Raman effect is now examined with the help of equipment worth almost millions of rupees. Chandrasekhar Venkat Raman was born at Tiruchirappalli in Tamil Nadu on 7th November 1888 to a physical teacher. Raman was a very sharp student. After doing his matriculation at 12, he was supposed to go abroad for higher studies. But after medical examination, a British surgeon suggested against it. Raman instead attended Presidency College, Madras. After completing his graduation in 1904 and MSc in Physics in 1907, Raman put through various significant researchers in the field of physics. He studied the diffraction of light, and his thesis on the subject was published in 1906. Raman was made a Deputy Accountant General in Calcutta in 1907 after a successful civil service competition examination. Very much occupied due to his job, he spent his spare time in the evenings conducting scientific research at the laboratory of the Indian Association for Cultivation of Sciences. On certain occasions, he even spent entire nights there. Such was his passion that in 1970, he resigned from the position to become the Professor of Physics at Calcutta University. On a sea voyage to Europe in 1921, Raman curiously noticed the blue color of the glaciers and the Mediterranean. He was passionate to discover the reason for the blue color. Once Raman returned to India, he performed many experiments regarding the scattering of light from water and transparent blocks of ice. According to the results, he established the scientific explanation for the blue color of seawater and sky. There is a captivating event that served as the inspiration for the discovery of the Raman effect. Raman was busy doing some work on a December evening in 1927 when his student K.S. Krishnan, who later became the director of the National Physical Laboratory, New Delhi, gave him the news that Professor Campton had won the Nobel Prize on scattering of X-rays. This led Raman to have some thoughts. He commented that if the Compton effect is applicable for X-rays, it must also be true for light. He carried out some experiments to establish his opinion. Raman employed monochromatic light for the mercury arc, which penetrated transparent materials and was allowed to fall on a spectrograph to record its spectrum. During this, Raman detected some new lines in the spectrum, which were later called Raman lines. After a few months, Raman put forward his discovery of Raman effect in a meeting of scientists at Bangalore on March 16, 1928, for which he won the Nobel Prize in Physics in 1930. The Raman effect is considered very significant in analyzing the molecular structure of chemical compounds. After a decade of its discovery, the structure of about 2,000 compounds had been studied. Thanks to the invention of the laser, the Raman effect has proved to be a very useful tool for scientists. Some of Raman's other interests were the physiology of human vision, the optics of colloids, and the electrical and magnetic anisotropy. Sir C.V. Raman became the Fellow of the Royal Society of London in 1924. A year later, he set up Raman Research Institute near Bangalore, where he continued scientific research until his death, which was caused by a strong heart attack on 21 November 1970. His sincere advice to aspiring scientists was that scientific research needed independent thinking and hard work, not equipment.
Thank you, sir. Now I request our Honorable Vice Chancellor, Dr. Upinder Dhar, sir, to welcome our guests by his warm words and gesture. Over to Dhar, sir, please.
Our distinguished speaker for this special day, Dr. Thalapil Pradeep of IIT Madras, Honorable Chancellor of the University, Shri Purushottam Das Ji Pasari, Honorary Secretary of the Vidyapeeth Trust, Sri Kamal Narayan Ji Buradia, all our trustees, directors of various constituent institutes, faculty colleagues, and my dear students. At the outset, I would like to extend a very warm welcome to our distinguished speaker, Dr. Pradeep. Today, 28th of February, is a special day because every year we celebrate the contributions made by great son of our great country, Dr. C.V. Raman. As has been already mentioned, 20th of February has been declared by the Government of India as the Science Day. So generally, if we see, the special day is announced on the birthday of the eminent person. But here it is an exception. 28th of February is not birthday of C.V. Raman. It is the day when his discovery was announced and which surprised the whole world, and ultimately there was no option than to recognize his contribution, and he was conferred Nobel Prize. We need to have a scientific temper, which is important. That is why in our university, right from the beginning, we thought that we should celebrate certain days in the name of the scientists who have made great contributions. And Sir C.V. Raman is one of them. Intention is to inspire the students and young faculty and learn from what has been done by our senior people. Unfortunately, generally, young students believe that all the discoveries, all the knowledge that we have today has come from the West. That's why we need to break that wrong belief. We need to spread the word that even this great country has produced great sons whose contributions were accepted, recognized, and also they were honored worldwide. Today, our distinguished speaker, Dr. Pradeep, will be talking about affordable water. And water is one of the most essential elements for life. All of us know that. That's why United Nations, while establishing 17 Sustainable Development Goals, identified that one goal, that is SDG 6, was dedicated to water and sanitation, keeping the importance of water in mind. All of us world over are concerned that how to provide affordable water, clean water, because SDG 6 is directly related to remaining SDGs. For example, health. How can health be ensured unless we are able to provide clean water to the people world over? That's what is a matter of concern. And by 2030, we have to achieve this objective of providing clean water to the whole world. That's why it's a very important subject. And we have a great scientist, great professor, Dr. Pradeep with us. And I'm sure that we will be having better understanding about this element by the end of this session. So with these words, I extend a warm welcome to Dr. Pradeep once again. Thank you very much.
Thank you very much, sir. To express our affection and reverence to one and all present over here, now I request our Honorable Chancellor, Shri Purushottam Das Ji Pasari Ji, to please address the August gathering. Honorable Chancellor, sir.
नमस्कार। चतुर्थ सर सीवी रमन स्मृति व्याख्यान के माननीय मुख्य अतिथि एवं वक्ता आदरणीय पद्मश्री डॉक्टर टी प्रदीप, प्रोफेसर, भारतीय प्रौद्योगिकी संस्थान मद्रास, सचिव श्री वैष्णव विद्यापीठ ट्रस्ट श्री कमल नारायण जी बुराड़िया, माननीय कुलपति श्री वैष्णव विद्यापीठ विश्वविद्यालय डॉक्टर उपेंद्र दत्त, श्री वैष्णव शैक्षणिक एवं पारमार्थिक न्यास के समस्त ट्रस्टीगण, समन्वयक विज्ञान क्लब डॉक्टर नीतू कटारिया, सभी संस्थानों और विभागों के प्रमुख और सभी विशिष्ट प्रतिभागी जो इस ऑनलाइन प्लेटफॉर्म के माध्यम से हमारे साथ मौजूद हैं, सभी को हार्दिक सुप्रभात एवं राष्ट्रीय विज्ञान दिवस की शुभकामनाएं प्रदान करता हूं। विशेष रूप से आज मैं हमारे मुख्य अतिथि पद्मश्री डॉक्टर टी प्रदीप का अभिनंदन करता हूं एवं शुभकामनाएं देता हूं कि उन्होंने हमारे बीच पधार कर हमारे विश्वविद्यालय का गौरव बढ़ाया है। राष्ट्रीय विज्ञान दिवस सर सीवी रमन द्वारा रमन प्रभाव की खोज के सम्मान में मनाया जाता है। देश के विकास के लिए वैज्ञानिक सोच का प्रसार आवश्यक है। राष्ट्रीय विज्ञान दिवस जैसे आयोजन वैज्ञानिक दृष्टिकोण के प्रसार में निश्चित रूप से सहायक सिद्ध हो सकते हैं। विज्ञान के द्वारा ही हम समाज के लोगों का जीवन स्तर अधिक से अधिक खुशहाल बना सकते हैं। बंधुओं, श्री वैष्णव ट्रस्ट एवं इसकी सहयोगी संस्थाओं ने गत 138 वर्षों से इंदौर शहर में नर सेवा नारायण सेवा मंत्र को आधार मानकर जन सेवा एवं जन कल्याण के अनेक प्रकल्प संचालित किए हैं। वर्ष 1884 में इंदौर के वस्त्र व्यवसायियों ने स्वयं के व्यवसाय पर शैक्षिक टैक्स लगाकर श्री वैष्णव सहायक कपड़ा मार्केट कमेटी की स्थापना की थी। इसका मूल उद्देश्य असहाय बंधुओं तथा जरूरतमंद नागरिकों की सहायता करना, पशु पक्षियों को आहार देना और साधु संतों की सेवा करना था। सभी पूर्ववर्ती संस्थापकों की दूरदर्शितापूर्ण नीतियों के क्रियान्वयन के फलस्वरूप संस्था द्वारा 1925 में श्री वैष्णव अन्न क्षेत्र की स्थापना एवं श्री रामकृष्ण बाग की स्थापना और 1934 में श्री वैष्णव आयुर्वेद औषधालय की स्थापना की गई थी। यह औषधालय विगत 87 वर्षों से आज भी संचालित है एवं इसमें आयुर्वेदिक, एलोपैथिक तथा होम्योपैथिक पद्धति से मरीजों का इलाज किया जाता है। 2015 में ट्रस्ट द्वारा 2 डायलिसिस सेंटर प्रारंभ किए गए। इसमें प्रति माह करीब 1000 डायलिसिस 400 रुपये के शुल्क से किया जाता है, जबकि डायलिसिस की कास्ट जो है 1200 रुपये करीब होती है। यह महसूस करते हुए कि शिक्षा समाज के तेजी के विकास और सुखी जीवन जीने के लिए अत्यंत आवश्यक है, 1951 में सर्वप्रथम वैष्णव हायर सेकेंडरी स्कूल की स्थापना हुई। आज ट्रस्ट के द्वारा 4 सीबीएसई स्कूल, 5 महाविद्यालय के पश्चात 2015 में वैष्णव विद्यापीठ विश्वविद्यालय की स्थापना की गई। वर्तमान में श्री वैष्णव ट्रस्ट के सभी संस्थानों में 23,000 से अधिक छात्रों अध्ययन कर रहे हैं। साथ ही ट्रस्ट के अंतर्गत 25 शैक्षिक और सामाजिक संगठन कार्य कर रहे हैं। उल्लेखनीय है, इन लाभ न हानि के आधार पर संचालित ये सभी संस्थाएं अपनी प्रतिष्ठा से संपूर्ण देश और प्रदेश को गौरवान्वित कर रही है। सन 2015 में श्री वैष्णव विद्यापीठ विश्वविद्यालय मध्य प्रदेश निजी विश्वविद्यालय अधिनियम के अंतर्गत स्थापित किया गया। विश्वविद्यालय का उद्देश्य ऐसा उत्कृष्ट शैक्षणिक वातावरण प्रदान करना है जिससे कि बौद्धिक, नैतिक एवं आध्यात्मिक प्रेरणा मिल सके एवं मूल्य आधारित नेतृत्व की क्षमता को पोषित किया जा सके। विश्वविद्यालय में हम कई नवीन पाठ्यक्रम का संचालन कर रहे हैं, जिसमें सोलर एनर्जी, बिग डाटा एनालिटिक्स, इंटरनेट ऑफ थिंग्स, मैकाट्रॉनिक्स, फॉरेंसिक साइंस, एग्रीकल्चर इंजीनियरिंग, आर्टिफिशियल इंटेलिजेंस जैसे कई नए कोर्सेस हैं। बदलते समय के साथ विद्यार्थियों को ऑनलाइन कोर्सेज तथा इंडस्ट्री की जरूरतों के हिसाब से भी नए विषय पढ़ाए जा रहे हैं। मुझे विश्वास है कि हमारा विश्वविद्यालय विद्यार्थियों को उत्कृष्ट शिक्षा प्रदान करता रहेगा एवं देश के भविष्य की नींव सुदृढ़ करने में अपना महत्वपूर्ण योगदान निरंतर देता रहेगा। महान भारतीय वैज्ञानिकों जैसे आर्यभट्ट, श्रीनिवास रामानुजन, सर सीवी रमन, विक्रम साराभाई, सर मोक्षगुड्डम विश्वेश्वरैया की स्मृति में व्याख्यान श्रृंखला आयोजित करने के विश्वविद्यालय के प्रयासों की मैं अत्यंत सराहना करता हूँ। ये व्याख्यान युवाओं को समाज के विकास में भारतीय वैज्ञानिकों के योगदान का स्मरण कराते हैं। साथ ही वे प्रख्यात वैज्ञानिकों और विद्वानों के साथ बातचीत करने के लिए एक मंच भी उपलब्ध कराते हैं। मैं इस ऑनलाइन मंच पर श्री वैष्णव विद्यापीठ विश्वविद्यालय में आज के वक्ता पद्मश्री डॉक्टर टी प्रदीप का पुनः स्वागत एवं वंदन करता हूँ। जल ही जीवन एक प्रसिद्ध कहावत है, परंतु यह तभी सत्य है जब पानी शुद्ध हो, अन्यथा यह कई बीमारियों का कारण बन सकता है। पीने के पानी को शुद्ध करने के लिए अमृत जैसी कम कीमत पर उपलब्ध तकनीकों के विकास से लाखों लोग लाभान्वित हुए हैं। यह मानवता के लिए आपका अत्यंत ही अमूल्य उपहार है। विज्ञान दिवस पर आयोजित चतुर सीवी रमन स्मृति व्याख्यान हेतु आपका आभार व्यक्त करता हूं और कामना करता हूं कि निकट भविष्य में आप हमारे विश्वविद्यालय का दौरा करें और हमारे छात्रों को उपयोग आधारित अनुसंधान हेतु प्रेरित करें। आपकी विशेषज्ञ सलाह निश्चित रूप से हमारे विश्वविद्यालय को बेहतर बनाने में मदद करेगी। यह मेरी प्रबल भावना है कि यह व्याख्यान निश्चित रूप से युवा मन को प्रज्वलित करने के उद्देश्य की पूर्ति करेगा। पुनः धन्यवाद। जय हिंद।
Thank you very much, sir. Now I request Head of the Department Physics, Professor Uttam Sharma, sir, for the reading of citation for Padma Shri Dr. T. Pradeep. Over to Sharma, sir.
Thank you, Dr. Neetu Kataria. It is a matter of pride privilege for me to read the citation for Padma Shri Professor Thalapil Pradeep. I quote, Professor Pradeep is a professor of chemistry at the Indian Institute of Technology, Madras, Chennai. He earned PhD degree in chemical physics while working with Professor C.N.R. Rao and Professor M.S. Hegde at the Indian Institute of Science, Bangalore during 1986 to 91. Subsequently, he spent about 2 years as a postdoctorate fellow at the University of California, Berkeley with Professor David A. Shirley and Purdue University, Indiana. Dr. Pradeep has conceptualized and built the International Center for Clean Water, an initiative of IIT Madras. He is the author of over 500 scientific papers in journals and is an inventor of 120 patents or patent applications. Access to clean water is one of the most important indicators of development, as water has to be affordable to make a meaningful impact on society. His work has led to the world's first nanotechnology-based water filter for pesticide removal, as many pesticides of relevance and halocarbons. He is involved in the development of affordable technologies for drinking water purification, and some of them have been commercialized. The technology named Amrit is being implemented now in the arsenic-affected region of India. More than 1 million people have been benefited from these installations. Several other drinking water technology have been rolled out from his lab. Dr. Pradeep is a recipient of Shanti Swarup Bhatnagar Prize, B.M. Birla Science Prize, National Award for Nanoscience and Nanotechnology, Indian Nanotech Innovation Award, J.C. Bose National Fellowship and National Water Award. He received the Kerala Sahitya Academy Award in 2010. He also received the Lifetime Achievement Research Award of IIT Madras in 2015. He is the winner of World Academy of Sciences Prize in Chemistry for the year 2018. He is also the recipient of Nikki Asia Prize 2020. President of India recognized his distinguished work in the field of science and technology by awarding him the 4th highest civilian award, the Padma Shri, in 2020. Dr. Pradeep is a fellow of Indian National Science Academy, Indian Academy of Sciences, National Academy of Sciences, Indian National Academy of Engineering, Royal Society of Chemistry, the World Academy of Sciences, and American Association for the Advancement of Sciences. He is associated as visiting professor with many national and international institutes. He has authored several books and as well as chapters in books on nanotechnology and chemistry. He is on the editorial board of many international reputed journals on nanochemistry and chemistry. He has authored popular science books in Malayalam. As part of his philanthropic activities, he supports a school in his village where 500 students are on roll. Shri Vaishno Vidyapit Vishwavidyalaya takes immense pride in honoring Professor T. Pradeep by inviting him to deliver prestigious 4th C.V. Raman Memorial Oration as a distinguished speaker on 28 February 2022, unquote.
Thank you very much, sir. Now I request our Honorable Chancellor and Vice Chancellor, sir, to present the citation to our Chief Guest, Dr. T. Pradeep. Thank you very much, sir. Now, not taking much time, I request our Chief Guest, Dr. T. Pradeep, to please deliver 4th C.V. Raman Memorial Oration on affordable clean water using advanced materials. Over to sir.
Thank you, Professor Sharma, for that kind words of introduction. Let me thank your Chancellor, your Vice Chancellor, also Neetu for your kind invitation and following it all through so that I'm here with you today. Science for me is an everyday thing. Science is what I have been doing all these years. For me, this is the only thing that I know today, because all other things have disappeared from me in this intense practice of the past several years. National Science Day is a day to celebrate science, celebrate Raman findings, celebrate the country, celebrate science as a whole. But science is not just a subject for celebration. Science is something to practice. And today, if I were to ask myself, what could be more exciting, or could have been more exciting in this past 58 years? For me, I'm 58 years old. The only thing that I can say is science. But that science is a totality, as your Chancellor talked about. It is not just science that we see as science and technology, but it encompasses every aspect of human endeavor, of human knowledge. I wish you success in all this. I chose to talk about affordable clean water. Affordability at one point in time, about 25 years ago. Before that, I had another phase of my life wherein I used to practice very basic fundamental science only for publication. 25 years ago, I asked this question, what is the science that I'm doing? And I said, how can this be used for certain use? And I picked up water as an important agenda at that point in time. Nanotechnology could be used for, let us say, many other things such as advanced memories, fast electronics, good diagnostic devices, better drug delivery vehicles. All of these are intensely practiced. But I thought I should pursue something closer to people. That is how I chose to talk about water, to work on water. But initially it was not funded, but subsequently we built companies on them. And so therefore, my advice certainly is to pursue something that you feel like pursuing, although it may not be initially recognized by the funding agencies or people around you. The subject of water is for me, for a chemist, it's a triatomic molecule. The molecule itself is exciting. And I studied this molecule and I continue to study this molecule in its beauty, in its complexity, using spectroscopy. But today's talk, I'm going to talk about larger water, not really this molecule. That water simply is the simplest and simultaneously the most complex problem of humanity. Everyone knows that we all came we all exist because of water. Biology exists because of water. But our economic, social, and cultural outcomes can all be traced to water. Water-rich countries are rich. Water-poor countries are poor. It's a very simple classification. And everything simplifies to water, including this lecture. There is a water cost associated with it. There's a water cost associated with internet. There's a cost associated with in power, in food, in clothing, as your Vice Chancellor talked about. All the sustainable development goals simplify to water because everything connects to water. And there is water in everything that we do. But that water has been a closed cycle for long. It was, so to say, a net zero cycle. And we got enough water from the rain. We circulated that water. It went back to rain, and civilizations flourished. But in the course of civilization, we opened that water cycle. And that the amount of water being so constant, it is just 33 into 10 to the power 45 water molecules on this planet. That appears very small, 10 to the power 45 or something. If you say it appears small, it is a billion tons of water. It's substantially big water. But that water is essentially constant, and we started contaminating it in many, many different ways. So there have been a number of methods to ensure that there is clean water available for people. Because the amount of water being constant and people kept on increasing, there is a need to ensure that clean water is available for all. That required new technologies. We also contributed to these. And that, I would say, putting several years of research, I would say that affordable clean water is a problem of advanced materials. In the course of civilization, we produce several materials. Nature has also materials. Materials are present on the surface of Earth, but these materials essentially give us clean water. Rain runs through this soil and gets you clean water because of the materials Earth is exposing to water. But our civilization, we have produced a number of materials. Distinct difference is that the solubility product of all of these is far different from the natural materials. Alumina and silica, they don't dissolve in water, and therefore you get clean water. But all of those we produce, they get into water. And in the course of their useful life and afterlife, they contaminate water. So we have created, through advanced materials, new adsorbents, new sensors, new catalysts, new phenomena, and several new devices. And this today is a subject matter of advanced materials, and that broadly is nanomaterials. And now today's lecture, I won't be able to get into all of those in great detail, but I'll take one or two specific examples and show you something interesting. But what has happened in this nanoscience and nanotechnology is that materials have become atomically precise. You see on the right side a particle. that is 25 atoms of gold with some ligands, certain number of ligands, having a charge very precise in molecular formula. So you can put it in a spectrometer, like a mass spectrometer, and measure its mass. The mass that you measure is 7390.5718, which means it is so precise, it is high resolution mass spectrometry. This is to tell you that you can create atomically precise pieces of matter in the laboratory, and they can examine them with techniques. So what does that mean? That means their properties can be examined too in great detail. So if, for example, when a contaminant is present in water, how does it interact with a particle could be analyzed in great detail to understand the science. And in the course of this science, we have applied a large number of, developed a number of materials, studied this process in great detail. So what does it give us? This is an example of what it gives you. This is a water pump, a 40-year-old cast iron pump working in Nadia district in West Bengal. And it is sitting on a cement platform, and this boy is pumping that. Water is coming from a depth of about 60 feet to about 80 feet. And water falls on, every stroke of this pump gives you 300 ml of water. And this water falls on the cement platform, and over the years, there is a red stain there to tell you that there is iron in the water. In this region, when there is iron in the water, there is a possibility that arsenic is also present in the water. Arsenic in this water is 60 parts per billion, or 6 times higher than the limits. It could be in another region, another slightly different, maybe at 10 meters, 20 meters away, it could be 200 parts per billion. Now, this water is, we knew about this arsenic contamination in water nearly for about 108 years. Not in India, in Argentina, we found that long ago. In India, this problem is known for about 60 years. But affordable solutions have not been there. Now, there may be many, many aspects associated with that affordability and usability, etc. But what we found was that several nanomaterials that we made in the laboratory could be put together, and without any pressure loss, without any additional burden on this boy who is pumping it, without any sustainability costs associated with it, you could get the 300 ml of water in just 2 seconds of contact, and that water is clean. It's not just arsenic is removed, many other contaminants are also removed so that the water is of US EPA quality or WHO quality. Now, at a cost, we said it should be less than 5 paisa per liter, but today at a cost less than something like 2 paisa per liter. And therefore, this kind of a treatment plant, this kind of a small thing, which can give you about 1,000 liters of water a day, or about for work in the field for 1.5 years without change of any parts or materials. Therefore, this has been implemented across and in several schools. So a school with 300 kids during the interval time can get water, or for coffee or their noon or meal or whatever. That is the basis of Amrit technology that your chancellor talked about. The basis of this is affordable materials, which we call water positive materials built on biopolymers. Take a step back and ask this question, what was the reason to introduce this? A large number of materials used for water, clean water applications, are produced in water. In the process of their production, they contaminate water. But in the process of their useful life, of course, they produce clean water. After their useful life, they go back to the field and they again contaminate water. So you ask this question, what is the net water outcome of this water? You find oftentimes it is negative. Therefore, there is a need to have water positive materials. Today, 1 liter of water used for the production of these materials can produce 500 to 1,000 liters of clean water. So that means 10 to the power 2 to 10 to the power 3 times water positive materials. The idea is very simple. You create porous materials, nanoscale porous materials, and pass contaminated water through and get clean water. What we do is biopolymers. And biopolymers can be a huge branch of materials. It can be chitosan, it can be cellulose, it can be banana silk, it can be very many different varieties. Nature is full of these. They act like templates, or they'll act like reinforcing agent. Think about cement, concrete mixture. Look, these biopolymers act like iron rods in them. And on these, you crystallize tiny flakes of iron oxyhydroxide. No, aluminum oxyhydroxide in this case. This can be very many different kinds of oxyhydroxides. Aluminum oxyhydroxide is one of them. And by selective control of these synthetic conditions, what you create is a template assisted growth of these tiny flakes. And if you look at them under a transmission electron microscope, you get pictures like these. These pictures suggest that they are tiny sheets. These are two-dimensional projections. So a sheet like these will look like a line in a transmission electron micrograph. Occasionally you see this, but mostly you see this. Now imagine these sheets are 6 sheets of this kind are kept together, 1, 2, 3, 4, 5, 6, you create a matchbox. And this is 50 nanometers long, 15 nanometers thin, and about 50 nanometers wide. And in these boxes, you can put nanoparticles. And these nanoparticles can be very many different types of nanoparticles, and you see them here. Now you start from a soluble material. In this particular case, soluble aluminum is used. And that is pH is controlled to create aluminum oxide, hydroxide. Hydroxide crystallizes and oxyhydroxide gets formed, and you create some kind of a sand-like powder. And you measure the properties of the sand. This is almost similar to river sand in its Young's modulus or any such properties. And so water can be put on top of it and it stays there for years together. So this is similar to the growth of calcium carbonate that you have in seashells. So this is with soluble carbonate ions, you create a matrix over a polymer template, which is a protein template in the case of seashells. You create such materials. What is so great? Let us say you put you put nanoparticles of silver. This releases silver ions, everybody knows that. And that is antibacterial, people know. But the silver particle, if you put it into water, real water, it produces silver ions, but in a few days, the silver ion concentration will come down. That is because the silver will be coated with this tiny layer of silicate, especially calcium silicate. And when that is a few nanometers thin, there is no more silver ion release, and the silver ion release concentration comes down. In this particular case, the release concentration is controlled at 50 parts per billion. That is the concentration that is required for antibacterial action, and not high, not low, but it is maintained not for 10 liters or 20 liters of water, but for thousands of liters of water. Now you run this, so you can ask this question, how do you run this experiment in the laboratory? It is impossible to run in this laboratory if you don't have a pilot production and a pilot testing facility to run water for 10,000 or 20,000 liters. So we converted, of course, in this slide, you can see a whole lot of history. How the lab transformed into a manufacturing facility. So when these ions are produced, live bacteria go dead. But you ask this question, well, nanoparticles are present. Do you have nanotoxicity? If nanoparticles are put into bacteria, bacteria pick up nanoparticles, and this is what nanotoxicity is about. These are individual particles you can see in the bacteria. However, In our case, although ion particles are there, only ions are released, and therefore ions are picked up by bacteria and they die. You don't see any particles. So there is no nanotoxicity present in this case, and you can study it with a number of other methodologies as well. So I told you about aluminum oxyhydroxide, but there can be many other oxyhydroxide. We put iron oxyhydroxide. So what is so great about iron oxyhydroxide? It's just that it picks up both arsenite and arsenate ions as effectively, as some other ion contaminant by another material. Let's say carbon picks up some pesticides or something. Aluminum iron oxyhydroxide picks up both arsenite and arsenate ions. Here comes Raman spectroscopy. We use Raman spectroscopy to ask this question: how is this arsenite and arsenate are picked up? Some details are there we will not get into, but these details tell us how they sit on the surface. So this is arsenite and this is arsenate, and they sit in a particular fashion, so we can model a nanoparticle and understand how they sit. So as a result, we can modify synthetic procedures to get better adsorption capacity. Sum and substance of this is that you put 100 parts per billion of arsenite and 100 parts per billion of arsenate, together 200, and you pass it through a small filter, about 12 to 20 grams of this material, and you see that arsenite concentration or arsenate concentration come down to less than 2 parts per billion. So we can clean up about 1,200 liters of water using that amount of material. So that is contaminated water, including iron, which gives you color, and you get clean water. So what it means is that you have a large capacity. So in a field which is supplying water in a 40 cents of land area, supplying water to about 2,400 people, making about 200,000 liters of water a day, 20 meter cube or 20,000 liters in an hour, 200,000 liters in a day, or 10 hours operation. You can shrink this whole thing to 3 cents of land area. These huge towers can be converted to something like 6 inches of towers. Prices can be substantially different. 168 ppb of input water goes down to 2 ppb of input water for the same amount of total water produced, while investment is substantially reduced. Okay, so we have implemented it. Many of these are arsenics, others are some other contaminants, etc., but across, and several other such implementations. And today it is no more, the first implementation was this plastic and all that. No, today it is all with cast iron devices across different parts of the country. I'll show you a brief 1-minute movie, how this is going today. So this is the total costing put together. With cost of replacement, cost of capital cost, etc., operational cost. Essentially, total price works out to 2.1 paisa per liter of clean water. Today, such sensors are put together, a number of sensors are put together on the water treatment plant, on the pipeline, at homes, etc. So this is now remotely operated as well. So here is a brief movie on that. So what I told you was the kind of technology that is about 3 years, nearly 3 years ago, that was implemented, and you saw 2021 February picture. Today, this is now operated remotely and with much more valves and control systems, etc. So this is when water is contaminated. You can clean it. But water is not, let us say water is not there at all. Then what do? You do atmospheric water harvesting. One of the things that we did was, using nanoscale materials, we created fibers. These are metallic fibers. They are similar to grass. The grass, as you know, like thorns, they collect humidity and dew condenses on them. Similarly, dew can condense on those nanostructures, and such nanostructures can be cooled and water can be drawn onto that, and you can collect water, and that becomes a startup company. So we have products starting from 35 liters of water per day to 2,000 liters of water per day. This, however, requires energy. But is it possible to have such a technology without energy, with just using sunlight? So that is, materials capture water in night, and in the daytime, when the materials are heated up with sun, water is released in an enclosure where the humidity increases, and the temperature, the humidity is such that the humidity condenses in the form of dew, you collect water. And such a thing requires only sunlight. It's also important to have other technologies. So we developed something called capacitive desalination, which is a technology for desalination similar to reverse osmosis, but with much more effectiveness, and amount of water reject is about 18% in comparison to 55 or 60% in reverse osmosis. Energy cost is also less. However, this requires a little larger capital cost today. So we developed new materials for that. The whole idea is to charge electrodes, positive or negative, and coat it with appropriate materials. These materials capture ions, oppositely charged ions, and you get desalination. The success of this technology will depend upon new materials. So we developed several new materials for better capture of ions. And that's a startup and activity, etc. I will leave through this, and I will leave through these as well. But the kind of science that we just now talked about requires analytical devices, several sensors. So today we have handheld sensors, which can measure concentration of several contaminants in water. But the way the world is moving is exciting. You know, this is a spectrometer sitting on a table, but today such UV visible spectrometers can become as small as this. And this is not ours. This is from a company with whom we work with to convert these into water quality sensors attached to a mobile phone. So you shoot a picture from your tap or right on your tap, and you get water quality. And this is where it is going. And what is it going to? So this is our Jal Shakti missions, Jal Jeevan missions dashboard. They are monitoring water quality, and several of us are also participating in this effort. And this is some region in Haryana. And each dot here has several communities. For example, this dot has 13 locations, and we measure water quality. And you see pH, pressure, chlorine, nitrate, TDS on a daily basis. Imagine what this is going to give us. This is going to give us water quality. This is going to give us water quantity. This is going to give us the health of the population. This is going to tell us the economics of the region. This is going to tell us many more things. And that is the way world is moving to. And that subject area will be called, that subject area will be called hydroinformatics. In order to take this science forward, we need to link the science with policy. Otherwise, this technology will not reach people. In the last 1 minute or 2 minutes, let me tell you where the world is going to. We know that 1 gram of water, 1 gram of H2, 1 gram of H2, when it oxidizes to H2O, it produces 286,000 joules of energy. 1 kilogram of hydrogen can produce that much more energy. You ask this question, how much of energy is needed for desalination of 1,000 liters of water? That's 1 cubic meter of water. Desalination requires about 2.4 kilowatt hour of energy, electrical energy. Now you ask this question, 1 kilogram of hydrogen, how much of clean water can it produce if desalination were to be performed? You will find that 16.5 cubic meters of water can be produced. 16.5 cubic meters of water can be produced by desalination using that hydrogen. How much will that cost for 1 kilogram of hydrogen? Mukesh Ambani says that by 2030, you can have 1 kilogram of hydrogen for $2. That would mean that 1 cubic meter of water can be produced for about 9 rupees. For 1 liter of water can be produced for 9 paisa, point less than, well, something like 9 paisa. No, I'm sorry, 0.9 paisa, right? 900 paisa, and you have 1,000 liters of water, 0.9 paisa. Imagine that world wherein hydrogen is produced from water and it is producing clean water. In that process, it is producing energy. And the whole world is run on this closed cycle of water to water. Water is used for hydrogen and it is producing water. And again, this hydrogen is producing water itself and no other contaminant that is produced. So water to water is a completely closed cycle. The only energy input is sunlight. Imagine that world. Imagine many other technologies. So we have built what is called the International Center for Clean Water at IIT Madras with this idea. The idea is that anyone can come with an idea into the center and build a water technology and walk with that technology. This is at the IIT Madras Research Park. It's a this whole research park is a 12 million square feet, 1.2 million square feet facility. And IIT Madras Research Park has many companies. Ours is a 22,000 square feet research facility. Many other activities are happening at IIT Madras. My work was supported by my students. Several of them are owning companies now, and with several governments, funding agencies, organizations across the country and elsewhere. And this whole work was possible because of the IIT Madras ecosystem. Today, that is well known for its innovation ecosystem. Thank you very much. I'll be glad to take questions if you have. Thank you.
Thank you very much, sir. Now I request audience, if they have questions, put in the question and answer sessions, and panelists.
You're audible, Sulbha Sharma.
Yes, hello, sir.
Hello.
I think you have already answered though. Like I have audible. Are there any members? Okay.
So I have a question. Can clean water be used like clean by affordable?
Can you please repeat the question again?
Can the seawater be made affordable drinking water?
Which water?
Seawater. Seawater.
Oh yeah, seawater desalination is not something that we have attempted with the Amrit technology. We have alternate technologies using capacitive deionization. We also have new kinds of membranes with nanomaterials, with increased permeation, with reduced rejection. These technologies are still not put in the field. We have several patents and publications in that area. We have not focused on that. The larger reason is that that's a highly mature technology and a lot of activity is there. But as I said earlier, if you can combine the best of membrane filtration technologies with new sources of energy, as I talked about for hydrogen, very highly promising can be found and implemented. We are just started in that direction, but those are interesting pointers.
Thank you, sir.
Hello, Professor. This is Dr. Namit Gupta.
Yes, sir.
Sir, in this region of Malwa Plateau,
Yeah.
the fluoride chloride levels are quite high in many regions.
Yes.
So, is your model applicable for that type of impurity removal also? The model which you have done for
Yes.
iron and arsenic?
Yes, fluoride it can address. It can address. In fact, it is being implemented also in several regions with fluoride contamination. However, one should note this point that fluoride concentrations are typically about 8 parts per million, something like, we are talking about 8,000 ppb in comparison to 500 or 1,000 ppb of arsenic. So it is like 10 to 15 times higher. So as a result, materials-based technologies will face challenges because they may not have adequate capacity to remove them. So therefore, one has to regenerate and things like that, which is again, which uses water. But with all that thing, in several regions, we have been in a position to implement. That is where it is not only fluoride, and fluoride concentrations are lower. I have students from Africa. See, there are places where fluoride concentration can be as high as 40 ppm. Material solutions are very difficult there. The only best solution is going to be in some form of membrane filtration or capacitive deionization. So we chose that in higher fluoride concentration, CDI is far more effective than these materials-based solutions, and we are implementing them. So water is not just one solution for everything. A huge multiple set of solutions, and all of them have their role to play. That is what I would say. In Malwa region also, I think we should implement multiple solutions.
Sir, I have one more query regarding the roof water trapping which we do.
Yes.
In Malwa area, there are many areas where the ground level water is very down, very low. So the roof water harvesting has come up with certain solutions. Now there are two major solutions which are generally provided by the people here. One is pouring the roof water directly into the borewell while passing it through a filter. Another one is digging a pit of say around 7-8 feet and then layering it with different materials. So I just have this query: which one is the better one for maintaining the groundwater level?
The latter one is better in terms of I would say it's protection of the groundwater's reservoir. In several places, our friends have analyzed the the benefits of both these, the direct recharging versus recharging through a recharge pit, and the benefits have been substantial on the latter one. Because industrial pollutants are there nearby, and our rainwater carry quite a bit. And we have found that this is indeed an issue. However, this is a kind of, one would say, one should take it with a pinch of salt. It's not that every region is contaminated or something. That is a wrong message to convey. So there are places where there are, let us say, mercury present in your atmosphere. As you know, there is a lot of coal-based plants produce plenty of mercury. These eventually end up in the rain. So there have been studies like that. It is easy to implement such solutions, as you said, and the cost is not prohibitively large. Our numbers suggest that it is about 16 to 17,000 rupees per 1,000 square feet of land floor area or rooftop area. That kind of water harvesting structures are being implemented by several of our people. They will be happy to implement in these regions also. Now, if that can be a solution with appropriate pre-filtration, why not?
Yeah.
Thank you very much, sir.
Thank you, sir.
Thank you very much, sir. There is one more question from Dr. Asmita Sharma. That is it possible in large scale that we obtained water from hydrogen and oxygen at normal condition at affordable cost?
Hydrogen plus oxygen giving you water, as I said earlier, the amount of water that is produced per kilogram of hydrogen, what do you produce? 1 mole of hydrogen will produce 1 mole of water, right? H2, 1 mole will give you half O2, giving you 1 H2O, right? That is only 18 grams of water. 2 grams of water will produce only 18 grams of water. 2 grams of hydrogen will produce only 18 grams of water. So this is not a great solution. Combustion is not a great solution for water, but combustion is a great solution for energy. Use that energy and do desalination in a big way. And the entire sea coast is full of sunlight. So that is the proposal that one is talking.
Thank you very much, sir. Now, gradually we reach to the end of the program. I request Honorary Secretary, Shri Vaishnav Vidyapit Trust, Shri Kamal Narayan Ji Buradia, to propose the vote of thanks. Over to Buradia, sir, please.
आज के हमारे इस अत्यंत ही महत्वपूर्ण कार्यक्रम 4th CV रमन मेमोरियल ओरेशन के मुख्य अतिथि एवं वक्ता माननीय पद्मश्री डॉक्टर टी प्रदीप, इंस्टीट्यूट प्रोफेसर ऑफ IIT चेन्नई, वैष्णव विद्यापीठ विश्वविद्यालय के माननीय कुलाधिपति श्री पुरुषोत्तम दास जी पसारी, कुलपति डॉक्टर उपेंद्र धर, डॉक्टर नीतू कोठारी एवं प्यारे छात्र छात्राओं, वैष्णव एवं सभी निर्देशकगण, विभागाध्यक्ष, शिक्षकगण एवं प्यारे छात्र छात्राओं, हमारे विश्वविद्यालय के लिए आज अत्यंत ही सौभाग्य एवं गौरव का विषय है, अत्यंत ही सौभाग्य एवं गौरव का विषय है कि आज हमारे बीच पद्मश्री प्रोफेसर थलपिल प्रदीप CV रमन मेमोरियल ओरेशन के मुख्य अतिथि के रूप में हमारे बीच उपस्थित है। CV रमन, जिन्हें की फिजिक्स में नोबल रमन इफेक्ट के लिए नोबेल पुरस्कार से सम्मानित किया गया तथा जिन्हें की भारत रत्न के सर्वोच्च पुरस्कार से सम्मानित किया गया, उनकी स्मृति में हम ये आज नेशनल साइंस डे के अवसर पर आज हमारे प्रदीप जी ने अफोर्डेबल क्लीन वाटर यूजिंग एडवांस मटेरियल पे हमको महत्वपूर्ण व्याख्यान दिया। IIT मद्रास की इस नई पहल एवं पेयजल शुद्धिकरण के लिए, पानी में से कीटनाशक हटाने के लिए पहला नैनोकेमिस्ट्री आधारित जो पानी फिल्टर बनाया है, वो हमारे देश के लिए अत्यंत ही महत्वपूर्ण एक उनका योगदान है। क्योंकि किफायती अफोर्डेबल अभी हमारे पूरे जो मोदी जी का जो चल रहा है कि पूरे देश में वो अफोर्डेबल स्वच्छ पेयजल प्रदान करना चाहते हैं हर गांव में, हर जगह। तो उसमें ये आपका योगदान सर अत्यंत ही महत्वपूर्ण रहेगा। इसको जितना ज्यादा से ज्यादा बढ़ाया जाए वो बहुत अच्छा रहेगा। तो सर ने एक बात कही कि उनके लिए तो आज साइंस डे नहीं, साइंस तो उनके लिए पर डे है। मेरे ख्याल से वो दिन प्रतिदिन कुछ न कुछ नई सोच के साथ हमेशा आगे आते हैं। सर मैं आपके लिए यही कहूंगा कि आपने एक देश के लिए और पूरे इसके लिए जो कि एक स्वच्छ जल हमारे लिए एक बहुत बड़ी चुनौती है और उसको पूर्ण करने में सर आप एक अपना महत्वपूर्ण योगदान कर रहे हैं। हम निश्चय ही आपके इस बहुआयामी व्यक्तित्व के प्रकाश से अभिभूत हैं। पूरा वैष्णव विश्वविद्यालय परिवार आपका इस हेतु अत्यंत आभार व्यक्त करता है। निश्चय ही आपके ज्ञान एवं अनुभव से हमारा ये उभरता हुआ विश्वविद्यालय समृद्ध हुआ है। निश्चय ही इससे हमारा विजन एवं रिसर्च क्षेत्र में विस्तार होगा। हमारा जैसा मालवा क्षेत्र सर जो है, यहाँ पानी की थोड़ी कमी रहती है। वैसे रेंज होती हैं लेकिन यहाँ रिचार्जिंग और इसके लिए बहुत ज्यादा, क्योंकि काली मिट्टी है तो एकदम पानी अंदर जा नहीं पाता, तो यहाँ रिचार्जिंग की काफी संभावनाएं हैं। मैं आपके लिए सर यही कहूंगा कि मिलते हैं मिन्नतों से ऐसे मेहमा, कभी कभी हो जाती है किस्मतें यूं मेहरमा, कभी कभी मिलती है किसी से प्रेरणा, कभी कभी हो जाती है किस्मतें यूं मेहरमा, कभी कभी। मैं आज के कार्यक्रम में उपस्थित सभी फैकल्टी, एचओडीज, कार्यक्रम संयोजक उत्तम शर्मा एवं ऋतु कटारिया एवं उनकी टीम का भी इस अवसर पर आभार व्यक्त करता हूँ। मैं वैष्णव विद्यापीठ विश्वविद्यालय के कुलाधिपति श्री पुरुषोत्तम दास जी पसारी, वाइस चांसलर डॉक्टर उपेंद्र दर जी का भी बहुत बहुत आभार व्यक्त करता हूँ। इस कार्यक्रम में उपस्थित सभी बंधुओं का भी मैं आभार व्यक्त करता हूँ। सर आपने बहुत बढ़िया कार्य किया है। हमारा इंदौर शहर भी स्वच्छता में 5वां स्थान प्राप्त करके अभी छठे उसके लिए प्रयासरत है स्वच्छता में। साथ ही पानी के लिए भी यहाँ पर एक सीवरेज, जो हमारी नदी, जो हमारा नाला है, उसको भी सीवरेज प्लांट के थ्रू काफी पानी को ठीक कर रहे हैं वो लोग। साथ ही यहाँ पर हम लोगों ने जो कचरा प्रबंधन के लिए एक बहुत बड़ी मशीन है, एशिया की सबसे बड़ी मशीन है, वो लगाई है, उससे सीएनजी पैदा कर रहे हैं। तो मैं आपसे निवेदन करता हूँ कि आप एक बार इंदौर पधारें और जैसा रिसर्च इंस्टीट्यूट आपने वहाँ डाला है, हमारे विश्वविद्यालय में भी ऐसे कोई प्रेरणा प्रदान करें कि हम वाटर के लिए कोई एक रिसर्च इंस्टीट्यूट हम रिसर्च इंस्टीट्यूट बना सकें। उसमें सर हम आपका सहयोग चाहेंगे और हम चाहेंगे कि आप इंदौर अवश्य पधारें और हमारे विश्वविद्यालय इस परिवार आपको इस हेतु आमंत्रित करता है। सर आपने कदम ऐसे रखे कि निशान बन गए और कार्य ऐसे किए कि पहचान बन गए। जीवन तो सभी जी लेते हैं लेकिन आप ऐसे जिए कि एक मिसाल बन गए। आपका इकबाल और बुलंद हो। आप देश की धरोहर हैं सर। आप देश एवं समाज की ऐसी ही सेवा करते रहें। आप स्वस्थ हों, शतायु हों। पूरा विश्वविद्यालय परिवार आपके सुखद एवं उज्जवल भविष्य की शुभकामनाएं प्रेरित करता है एवं इंदौर में आपको आमंत्रित करता है। हम सभी आपका पुनः वंदन करते हैं, अभिवादन करते हैं एवं आपने जो हमें समय प्रदान किया वो इतने अच्छे ढंग से हमें सब पूरे वाटर के बारे में इतने अफोर्डेबल शुद्ध वाटर कैसे पाए जाए उसके लिए जो आपने बताया सर, उसके लिए बहुत बहुत धन्यवाद। जय हिंद। आभार, पुनः आभार।
Thank you very much, sir. I once again thanks to all the dignitaries and delegates present through this online platform with us. Thank you very much, sir. I request all of you to please stand up for the national anthem.
जय गण मन अधिनायक जय हे भारत भाग्य विधाता। पंजाब सिंध गुजरात मराठा द्राविड उत्कल बंगा। विंध्य हिमाचल यमुना गंगा उच्चल जलधि तरंगा। तव शुभ नामे जागे तव शुभ आशीष मांगे। गाहे तव जय गाथा जन गण मंगलदायक जय हे भारत भाग्य विधाता। जय हे हे
Thank you, sir.
Thank you very much,
Hello.
Dr. Pradeep. Thank you.
Thank you, sir.
नमस्कार सर.
See you next time. See you next time.
Thank you very much, sir. Thank you, sir. Thanks for accepting our invitation.
Happy to come there, and let's see what we can do. Yeah.
Yes, sir.
Yeah,
Yes.
sure.
Thank you very much. So shall we end the program?